In this video, we're going to talk about absolute maxima and minima. So we talked about local extrema before. So the value f of c is called a local maximum if there exists some interval containing c such that f of x is less than or equal to f of c for all x in a in that interval. The value of f of c is called local minimum if there exists an interval a, b containing c such that f of x is bigger than or equal to f of c for all x in that interval. So those are local minima, extreme, or local minima and maxima or extrema. And the point is, with a local extrema, if I draw a picture, you might have a situation like this. There's a local max, there's a local min. So this is a local max and this is a local min, but over here the function is lower than it is here. So it's not a global minimum or an absolute minimum because there are places in this function which are less than that. And this is not an absolute maximum because over here there are places which are, for this function, which are bigger than that. But in a region around these points, this is locally a maximum and locally a minimum. So we define absolute maximum and absolute minima as follows. If f of c is bigger than or equal to f of x for all x in the domain of f, then f of c is called the absolute maximum. And if f of c is less than or equal to f of x for all x in the domain of f, then f of c is called the absolute minimum. So if we draw a picture, here is an absolute maximum. Here is an absolute minimum. So these are absolute extrema. Now, absolute extrema are clearly local extrema as well. So let's find the local extrema of these functions and see whether they're absolute extrema as well. So f of x equals 1/3 x cubed minus 4x. So what do? We take the derivative. We're going to find critical numbers. So that's 3x squared minus, just x squared minus 4. Find out when this is 0. So this is 0 equals x squared minus 4. X equals 2 or x equals negative 2. Okay, so our local extrema are f of 2 and f of negative 2. So f of 2, that's 1/3 of 8 minus 8. So 8/3 minus 8, whatever that is. And if we put negative 2 in here, we get negative 8/3, negative 8/3 plus 8. So these are our local extrema. But if we think about this function, right, if we put in a really, really big positive number, then f of that really big positive number is an even bigger positive number. And so that's going to be bigger than, let's see, f of negative 2. And to be honest, f of 2 as well. And then if we put in a really big negative number, we're going to get a really big negative number out. And so these are local, but not absolute. F of x equals x to the 2/3. Well, again, we do the same thing. Take the derivative, 2/3 x to the negative 1/3. Critical numbers are when this is 0 or not defined, assuming the function is defined. So we have a critical number at x equals 0. And let's see, we could take the second, well, it's not defined, so that's not going to help us very much to take the second derivative there. So let's just look for a second at a number chart for f prime of x. It's a critical number at 0. If if x is less than 0, really big negative number, this is negative, so it's decreasing. If x is bigger than 0, put in a really big positive number, this is positive. So we know the function is decreasing, then increasing, which means that f of 0 is that's equal to 0 is a local min. Now we ask ourselves, is this an absolute min? Well, to figure out whether it's an absolute minimum, we think about, okay, well, the only place where this changes directions, where this function changes directions, is at 0, right? From increasing to decreasing or decreasing to increasing. From 0 to the right, this function is always increasing, which means to the right, f of x is always bigger than f of 0. To the left, this function is always decreasing, which means to the left, f of x is also always bigger than f of 0. So that means that f of 0 must be an absolute minimum. Okay, so in this first one, we had local minimum and local maximum, which were not absolute. In the second one, we had a local minimum, which was also an absolute minimum. All right, so we have something called the extreme value theorem. So a function that is continuous on a closed interval, a, b, has both an absolute maximum and an absolute minimum on that interval. So this is known as the extreme value theorem, and this is basically, this kind of makes sense, right? If we choose some interval and it's closed, a to b, then no matter what the function does, it must achieve a maximum value and a minimum value somewhere on that interval. Now it has to be continuous, and it has to be a closed interval, because you could always, with an open interval, you could always have a function, let's say, that just went up to infinity, right? And then doesn't achieve an absolute maximum because it keeps getting larger. It doesn't achieve an absolute minimum because it never actually gets to 0, for example. Okay, so absolute extrema, if they exist, must occur at critical numbers or at endpoints. Again, look at our picture. The places where it could happen are here. There's a critical number here. This is the endpoint. Critical number, critical number, critical number, critical number, endpoint. Only places it can happen. So, to find an absolute extrema, what do we have to do? Make sure the function is continuous, find the critical numbers, evaluate the function at the endpoints and at the critical numbers. The absolute maximum is the largest number you found, and the absolute minimum is the smallest number you found. So, 1, make sure you're continuous. 2, find the critical numbers. The critical numbers are either where the function, the first derivative is 0 or not defined. Evaluate the function at the endpoints and at the critical numbers and check which one's biggest, that's your absolute maximum, which one's smallest, that's your absolute minimum. Let's do an example. So we want to find absolute extrema for f of x equals x cubed minus 21x squared plus 135x minus 170 on the closed interval for 8. So first, this is a polynomial, so it's continuous on this closed interval. Second step, find the critical numbers. Critical numbers are where the first derivative is either 0 or undefined. 3x squared minus 42x plus 135, nice numbers. Set it to 0 because this is continuous, equals 3x squared minus 42x plus 135. Divide it by 3 and we get x squared, let's see, minus 14x plus 4, and that's 45. All right, 45 is 9 times 5. Okay, so we're going to get equals x minus 9 and x minus 5 is 0, which means x equals 9 or x equals 5. The only one we care about is x equals 5 because we're on this closed interval. So what we need to do is evaluate f of 4, f of 5, and f of 8. All right, if we evaluate those 3, we will figure out where we have absolute extrema. All right, let's get a calculator out. Let's make it a little smaller so we can see. Okay, so f of 4, which is 4 cubed minus 21 times 4 squared plus 135 times 4 minus 170, 98. So f of 4 is 98. Okay, f of 5. F of 5 is 125 minus 21 times 25 plus 135 times 5 minus 170, 105. So f of 5 is 105. F of 8. 8 cubed minus 21 times 8 squared plus 135 times 8 minus 170, 78. All right, so f of 8 is the absolute min, and f of 5 is the absolute max. We look at our values and we see which one's biggest and which one's smallest. So that's our process. Okay, second derivative test for absolute extrema. So this is a test we can use if very certain conditions are met. So we want f to be continuous on the interval ab, open interval, with only one critical number in that open interval. If f prime of x, f prime of c equals 0, and f double prime of c is bigger than 0, then f of c is the absolute minimum. Remember, f double prime of c bigger than 0 means we've got a smile. F prime of c of 0 means we're here. There's only one critical number, so it must be decreasing, then increasing, so we have an absolute minimum. Equally, if f prime of c equals 0 and f double prime of c is less than 0, remember we have a frown, then f of c is an absolute maximum. So let's do one more example. On the interval 0 to infinity, find the absolute extrema of f of x equals x plus 4 over x. First off, f of x is not defined at 0, which doesn't matter because we're on the interval 0 to infinity. Okay, so let's take a derivative. We're going to find the critical numbers. F prime of x equals 1 minus 4 over x squared. Set it to 0 equals 1 minus 4 over x squared. Again, remember x is not 0, so we're okay. So 4 over x squared equals 1. X squared equals 4. X equals plus or minus 2. The only critical number we're interested in is x equals 2 is our critical number. Right? The other one is not in the interval. So we have one critical number. So it's either an absolute max or it's an absolute min, depending on the sign of the second derivative. So let's take the second derivative of this function. F double prime of x equals, let's just rewrite this to make our lives a little easier, 1 minus 4x to the negative 2. It's just easier to look at, right? So that's going to be 8x to the negative 3, right? We bring the exponent down, negative 2 times negative 4 is positive 8. Decrease the exponent by 1, x to the negative 3. F double prime of 2 is bigger than 0, right? 2 to the negative 3 is 1/8, so it's actually equal to 1. But it doesn't matter what it's equal to, it's just the sign that matters. So this is bigger than 0, which means, again, we have a smile. It's concave up, convex. Given that it's a smile, this must be an absolute minimum. So this is how we solve these kinds of problems. If there's one, we're on an open interval. If there's one critical number, it's either an absolute max or it's an absolute min. You've got to check the second derivative. If we have more than one critical number on a closed interval, then you check the endpoints, you check all the critical numbers, evaluate your function, and you see which one's biggest, that's an absolute max, which one's smallest, that's an absolute min.